hello. What we bring today is how can you use autonomous driving algorithms to solve your business challenges. So more specifically, what we bring today is actually how can you use multitask learning to solve your business challenges. And we are doing this because it already added value for us, and we believe that these kind of algorithms can be a good challenger for other algorithms. And what are these other algorithms? So on a supervised learning context, so where data is labeled, what we typically find in most use cases is a single task learning, so a single task model. And what is this single task model? So it's a model that you provide some independent features, you provide the labels or the target, so the dependent feature, and then during the training phase, it's able to link an observation to a category of the target. And the model does this by optimizing one loss function. And after the model is trained, you can provide new observations, and the model will give you a category of the target for that new observation. So it's a model that answers to one business question and one only business question. However, when we look at this picture, that is taken out actually from a Tesla presentation of a PyTorch conference, you see a lot of tags on this image, because this is a very simplified version of what the autonomous vehicle actually sees. So you will have traffic lights, you will need to identify the road signs, you will need to identify the static objects, moving objects, and so on and so forth. And you will even actually need to identify like the environment tags. So if the vehicle is in a residential area, or if the vehicle is in a tunnel. So there are like a lot of tasks here. And the colleagues that are tackling this issue, they kind of have two options. So they actually have like a lot of single task learners, so one model for one task, or they actually use these multitask models. That, for now, let's just agree that it's a model, so one model that provides inferences for several tasks at the same time. And of course, there are like several reasons why these companies like Tesla and so on, they use multitask models. I will just tackle two because I think they are like the most important ones. So the first one is all of these inferences are done in the cores that are available in the car, in the vehicles. And inference time is really, really important. So the vehicle cannot wait like a lot of time for these kind of inferences. So it's much faster for you to provide an inference on one model that provides several outputs that actually to provide many inferences from many models. Another thing is the model performance. So the model performance, these kind of companies, they will have, so the vehicle will have like people inside, so lives are at stake. So the 97% level of accuracy is really not enough. So they really need to be on the 99.9999 level. So they actually learned that with the multitask models, under specific and certain conditions, you can overpass the model performance of the single task ones. And let's talk a bit about the multitask model. So, like I said before, this is a model that provides inferences for many tasks. And how can you actually do this? So, for each task, you provide the features, the independent features, you provide the labels of each task, and one loss function. So each task here will have one loss function. So if you have 3 tasks, you'll have 3 loss functions. And then the model will optimize all of these loss functions simultaneously at the same time. And when the model is trained, you can give a new observation, and it will provide like the inferences for all the tasks that you trained it for. So it's a model that, contrarily to the single task learner, can provide answer to many business questions at the same time. This can be, we will focus on this presentation, how can this be applied to deep learning? It can be applied to other things, but let's focus on the deep learning. So, we will focus actually also on the method of the hard sharing parameters. The hard sharing parameters proposes an architecture that has like a shared backbone where the features representation are learned and they are shared to each one of the tasks. So you have like one shared backbone, one body, and many heads, and each head of the neural network is related to one task. Actually, the multitask models of Tesla, they are called Hydra nets, because it's like the Hydra from mythology. They have one body and many heads. So it's exactly like this. And then you can ask, okay, so why this works? So imagine that you go to a museum and you are observing like some art piece, like a sculpture or something like this. So it's really pretty, really detailed, and so on and so forth. But let's say that you can only see it from one point of view. You still find it pretty, you still learn from it, you are observing it. But actually, if you move around the room, right, you will see many more things. You will capture much more information. So the multitask learning is exactly this. So each point of view is a task, and the sculpture, it's like your data. So these shared feature representations, it's done in such a way that the model learns more generic and more useful features because it learns all the tasks at the same time. So this is one benefit of using this kind of architecture and modeling. Another thing is, since it's learning generic features, it also discourages overfitting, right? And then another benefit is that, let's say that you have a task that is abundant with data. And then you have another task which is scarce with data. Actually, since these models, they learn from the complex data relationship, but also from the task relationship, the task with scarce data will learn from the task with more data. So this is another benefit. But of course, like, there are challenges. And one of the challenges is that not all the tasks can be trained together, right? So we'll talk about this later. Another thing is the problem framing. So this is different from the problem framing than the single task learners. And another thing is the weights that we give to each loss function. So we need to properly take care about this. And it's about the loss function. So like I told before, each task will have its own loss function. But actually what the model sees, it's one very special loss function that is an aggregated loss function. And since each loss function might be in different scales, first you need to balance it for the same scale. Another thing is that you need to give proper weights to the tasks that you are learning. For instance, the data imbalance thing that we talked about, you can give here more weight so that the model gives more attention to the task that has scarce data. And now the million-dollar question of the multitask learning. So which tasks can actually be learned together? This answer is quite simple. So the tasks that are related. Why? Because they share a positive transfer between themselves, allowing the multitask model to overpass the single task ones. And let's just define two types of tasks. So the main task is actually the task that I care about, that will solve my business problem. And the auxiliary task is a task that I define that works as a copilot, as a wingman, as a wood stick for the model to better learn my main task. Let's suppose that I have two tasks, and let's take the example of the autonomous vehicle. Let's say that I want to predict the steering direction, and I want to detect the road lines. So these are, of course, related, because I cannot properly steer the vehicle and not take into consideration the road lines. But let's say that you have like 100 tasks. So this is like the difficulty is exponential here. So for you to understand which tasks can be learned together, there are like good frameworks. For instance, not all the tasks can be learned together. You might end up with one multitask model that is with a set of tasks, and another multitask model that is with another set of tasks. And there is this very good framework from the colleagues of Stanford that they try to map like an affinity matrix between the tasks, and then they try to solve it as an optimization problem. But now let's say that you only have like one task, okay? You can solve it with a single task learner, or you can actually solve it with a multitask model. How can you do this? You can actually define an auxiliary task for your main one that will help the model to better learn the main one. And then you need to, of course, don't forget to go to the loss functions and properly calibrate the weights, because you care about the main task and you care less about the auxiliary one. And I hope you have all seen Karate Kid. When we were learning about this multitask learning, we ended up reading a paper that actually helped us to better understand what is an auxiliary task. The story of this goes like Daniel-san, which is the youngest guy, wanted to learn karate. And Mr. Miyagi, which is the elder guy, gave him somehow, for Daniel, seemed like unrelated tasks. And anyway, Daniel did it. And when he was like waxing the Mr. Miyagi's car, he was learning like some kind of movements that when he tried to practice karate, he actually could use those same movements and learn karate better. So the waxing on, waxing off, it's actually like an auxiliary, like a co-pilot, like a wood stick to learn the main one, which is the karate. Now, an example of success of related main tasks. The team of Mr. Poplin, they wanted like to have like some kind of indicators based on the retinopathy image, so an exam, medical exam made to your eye. And they had like single task for each indicator, so something like the age, the blood pressure, if the patient was a smoker or non-smoker, the gender, and so on and so forth. And what they learned is that when they put all of the tasks together and they used a multitask model, the metrics that they obtained, they overpassed the single task models. So it's another example of success. And now, coming to our use case. We are a bank, right? And we have clients, and our clients make transactions. Some of those transactions are transfers, so something like you are sending money to your mother or father or sibling or whatever. Another type of transfers are payments of service, so things utilities that you pay. And another one is the top-ups for your cell phone. And our goal in our use case is to predict the next transaction of our clients so that we can anticipate our client needs and remind them in due time for them not to forget to do that transaction. So based on the sequence of transactions of each client, what we want to predict is to whom will the next transaction be and when will it be. So 2 targets, right? This is a natural fit for a multitask model. And our model, the way that we imagine it, is also based on the hard shared parameters methodology that has like this common backbone and then 2 heads. 1 head for the beneficiary, which is a classification, and then another head for the date, which is a regression. Last but not the least, so independently of the model that you use, of course, you need to take proper care of the features and perform feature engineering on your exercise. And besides the targets that you already defined, we also define like exogenous features, something like cyclical encoding of time features, so sine and cosine of the number of the day and of the number of the month, time elapsed since defining events, so for instance, how many days have already passed since the last payday of each client, then z-score calculated features, and then features related to the client at the time of the transaction. And talking now a little bit about our model architecture, we have sequences, so we use LSTM layers, more specifically bidirectional LSTM layers, and then the outputs of this, so the shared feature representation is made available at the same time to the dense, to the beneficiary head and to the date head. For the beneficiary head, we used sparse categorical entropy as loss function, and for the date head, we use Uber loss because it's a regression. And what we realized is that when we were training the model, the model somehow better learned the beneficiary than actually the date. So the date was more difficult for the model to learn. And we needed to make like an adjustment. So we kind of provide a higher weight for the loss of the date than of the loss of the beneficiary. And we did it by updating the loss function so that the model can give more attention to the date, to the date of the loss, to the loss date, sorry. And now we only need to say one more thing about this. So our success metric. So our success metric is each prediction needs to have the correct beneficiary, and the date output needs to be within a 2 days time frame. And of course, we solve this also with single task learners. And with single task learners, we obtained around 70% of accuracy. And with the multitask learning model, we achieved 83. So we kind of have 13% more of accuracy with the multitask learning model. And the model is in production. It's available to our clients, and we are actually very proud of it. We really hope that you guys feel inspired and challenged in using this multitask learning model. But there are like a lot of AI breakthroughs right now, and it's important to be creative and to stay keen on this in order to find new solutions. Thank you.
Okay, thank you, Tiago. We have a couple of questions.
Perfect.
The first one is, you showed one way of combining the loss functions. Have you tried different ways? Does it matter?
There are more ways to combine the loss functions, of course. We need to just to take care that it's an aggregation. So the model itself only sees one loss function. But what's behind it, we can adjust and manipulate according to our needs. Yeah.
Okay. Another question is, have you tried this on tasks that are related but don't share the same set of attributes?
Actually, for this use case, we did not, because they actually share the same attributes. But there are, let's say, more methodologies besides this hard sharing parameter. So something called like the soft sharing parameter. And this one is actually more indicated for that don't share the same data coverage. But in the end of the day, the most important thing is that the affinity of your tasks is positive. So you need to have positive transfer between the tasks. Otherwise, it's better to learn them independently.
Let me clarify. So, but the morphology of the data set, so the attributes are always the same, right?
For this case, yes. Yeah, the same features.
But have you tried with data sets which didn't have tasks that didn't have exactly the same?
For this use case, no, because they have. But in case you need to, there are like this soft sharing parameter methodology that can better cope with that need.
Let me see. Sorry about this. Another question. I have a few. So there was a clarification here about how did how did you evaluate these models?
Yeah, so we evaluated these models. Our metric was, in the end of the day, the accuracy. So let's say we are predicting that the client will make a transaction. And we know, first of all, if the client did the transaction. And we also know if the client somehow responded to our teaser, because this is available on the app. So this is how we know if our prediction was useful or not for the client.
And as part of that evaluation, do you do things like A/B testing, or everybody?
Yes, of course.
Okay.
No, of course. But we do A/B testing with everything. So this is like methodology that we use, of course.
Okay. For another question. One question. We had to have a question about transformers, of course. Why not transformers?
Yeah, why not? Yeah, it can be used.
You haven't tried it?
No, we didn't try this one. We can do it. Actually, I mean, even CNNs can be here. So yeah.
You think it doesn't matter?
Again?
You think it doesn't really matter?
No,
the model, the sharing is important.
The point that we wanted to show here, it's like this way that the tasks can be jointly trained. So how you build up the shared backbone, it needs to be in accordance to what your needs. Yeah. In this case, we used bidirectional STM layers. but you can use, of course, transformers. Yes.
Oh, I have a question that kind of anticipates one of the next sessions. Is about interpretability of decisions. So you're using these neural networks.
Yes.
And do you deal with this issue of interpretability of the decisions, or in this case, it doesn't really?
It's important for us to always understand the feature importance.
Okay.
And we did it in this case. So even though you have like one shared backbone with two heads, if you, after you train, you freeze all the layers and obtain all the weights of the neural network, you can actually build two deep nets, right? And in the end, with game theory, you can understand the most important features.
There are a few more questions, but I think we're really out of time.
Okay.
So thank you very much, Tiago.
Thank you. Thank you.